Hello everyone, this is our PHY 1111 and we're going to be talking about rotational motion, dynamics of rotational motion. So we've got, I think I want that there. We want, all right, so we want to go on the Price is Right. And we want to get that wheel. We want to get to the point where we get to spin the wheel on the Price is Right. So there's this wheel. And it's got all the good numbers on there. It's got a whole bunch of them. It's got the 100. It's got the 100 on there. Anyway, it's got these sweet numbers. And it's going to spin around. And some person's going to grab it. They're going to grab it by a handle. And then they're going to pull down. Okay, so that'll be the force of the person pulling on the wheel. The wheel has a certain radius, r, and that force of the person can be totally perpendicular to the radius. So if we draw the radius like this, and we draw our force, we can put and make sure that the force of the person, not sure what happened there, but we can make sure that the force of that person is exactly perpendicular to the radius r. Okay, so the angle between them is pi over 2 equals 90 degrees. Very nice. So, person's going to pull. They're pulling down. They're going to give it a force. And what is this thing going to do? It's not only going to have it's going to start from 0 with angular velocity, and then it's going to go up to something, right? So who knows what the final angular velocity will be, which means whenever you have a change in the angular velocity over time, you have an angular acceleration. Okay, so that's what we're dealing with, is angular acceleration. Okay, so how do we find alpha? All right, well first, the force of the person is equal to our mass times our acceleration, and that equals our mass times our radius times alpha. Okay, so if we know the mass of the wheel, the big wheel, the winning wheel, if we know the mass of the wheel and we know the force of the person, we can solve for alpha by saying the force of the person divided by our mass of the wheel and the radius of the wheel. All these things are measurable for the most part. I mean, the force of the person we could measure, or we could figure or guess or whatever. But at any rate, you can come up with your alpha from there. Now, what if we want to know what the torque is? So, the torque. How do we get that torque from alpha, r, and m? Well, it turns out not too difficult, because what is torque? Torque is equal to r times the force, especially, we're not going to put the sine of 90 in there because the sine of 90 degrees is 0. Technically, it's this, right? The sine of the angle between these two. But since that is 90 degrees, the sine of 90 degrees is 1. So we have just the radius times the force that we're applying. So there's our force person. And I'm gonna leave that off. Okay, so our radius times the force of the person, which equals our radius times m times r times alpha. So really, our torque is equal to mr squared alpha. So that is pretty much what we saw earlier today in class. And we can say that this bit right here is our moment of inertia. So we give it a capital I for the inertia bit. So we say that that is equal, the torque is equal to I alpha. And there you go. So our moment of inertia is that. Now, so we've talked about it a little bit in class. I just want to reiterate. When we're dealing with forces, force is mass times acceleration. This is our inertia. And the analogous rotational thing is torque. And torque is our moment of inertia times our angular acceleration. And this is just our straight up acceleration over here with the force. Okay, so we've got angular acceleration, we've got acceleration. We've got moment of inertia, we've got inertia. These guys over on this side are the rotational versions of these guys, which are the linear. So we've got linear, translational, and over here we've got rotational or angular. Okay, so far so good. Okay, so let's see. How do I want to do this? We want to look at a well, we did it for the moon. We don't need to necessarily do it for the moon again. Let's do it for a disk. Do you guys remember CDs? Okay, it's like a donut. From this angle, it looks like a donut, but it's really a CD, and it spins around an axis right in the center. Okay? And, or a record, or I don't know, whatever you guys want to think of, a cylindrical object. All right, so it's thin, it's cylindrical. Here, look how thin it is. This is from the side. You can't see the hole in the middle because you're looking at it from the side. Pretty thin. Okay, so let's look at a piece. We'll pick this bit right there, okay? So somewhere there's a little bit that we selected right there. And here's the axis. So there's a distance to that little piece, and let's call that distance r. So this is the distance r. Okay. Nice. Well, the whole point of all of this is that we can take that little piece and we can figure that its angular momentum for the little piece is equal to the mass of that little piece times the radius that little piece is from the center, and we need to square it. Don't forget, you got to square that, right? So let's make sure we go back up and notice that we have to square it. Okay, so our m of the little piece times r, how the distance squared. Okay, so that's our I for the little piece. Now, we've cut it up into that little piece, but we want the whole thing, right? We want the entire, the whole enchilada, the whole CD, the whole record. We want all of it. So we've got to do it for all the little pieces. And who knows how many pieces there are. We're going to add them all up till we finally get to the last piece, the nth piece. And that is going to equal, we add it all up, and that equals the moment of inertia for that object. Okay? Well, that's not always easy to do. So I'm not sure how many of you are taking calculus right now, but this is what calculus is designed to do for us. And essentially, we're saying I equals 1 to n of all the little moments of inertia, okay? So we're summing up all of the little bitty ones to get to the whole thing. Okay, well, we're not going to do it that complicated. We're going to make it easy on ourselves. And we're going to do an example where we have a dumbbell. So we've got a bar. We've got two masses on the end of the bar. And they're the same size. I don't know why they don't look like that, but, well, maybe they're not. Who knows? We've got a pivot point, okay, right in the middle. We've got L over here, L over there. So the distance to the center of those masses is the same. And our total I is going to equal the I from 1 plus the I from 2. So the moment of inertia for 1 plus the moment of inertia for 2 is going to be our total moment of inertia. And so let's start plugging in what I1 is. I1 is equal to mass 1 times the length squared. Okay, so let's look at I2. I2 is equal to mass 2 times its length squared from the rotational point, right? This is the point of rotation, all right? So that is L for each, and we're going to square it. Okay, good. So we can then get I total equals I1 plus I2, that's just M1L squared plus M2L squared. And of course we can factor out the L, so we get L squared and M1 plus M2. And that's our I total. Okay, now, what if those M's are equal to each other? If M1 equals M2, we'll say that that's M. Then we have two of them. So now our I total equals 2ML squared. So for a dumbbell, we have just gone through and figured out what the moment of inertia theoretically should be. Okay, so we talked about it in class, and I showed you some. And I'm not sure which book you have. So there's two books. There's the new edition, the 2E edition. All right, second edition book. That book is what I'm about to show you. The old 1E edition has this, the figure is 10.12. That's the one I talked about in class because that's the one I have on my computer. However, let's go to this. This says that it's figure, you can see down here on the bottom, figure 10.11. Okay, so this is 2E. This is the newest, the latest and greatest. Same picture. So, okay, but if you notice, let's talk about the top left. Okay, let's say we have a hoop, and it's just this hoop. It's got a mass. The hoop has its mass times the radius of the hoop squared, and if it's rotating about that axis, then that's going to be its moment of inertia, the mass of the hoop times the radius squared. If we have an angular cylinder, so that there's two radii. There's one to the inner radius and then one to the outer radius. So we're going to then take the whole mass of the object, we'll divide by 2, and then we square the inner radius and we add the squared outer radius. Now, don't get me started on why we're adding and not subtracting or blah, 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 any of that other stuff. Because, like I said, you need calculus to go through and figure out how to get these things. However, it's doable, not terribly difficult. One that you're going to use quite a bit is this one, where you'll have to the left, second one down on the left. It's a solid cylinder or a disc, right? Because it could be a thin disc. This little L, the length of the disc, could be small. And it's rotating about, it's a cylinder rotating on its axis. That is 1/2 mr squared. Okay, so a solid cylinder or disc, 1/2 mr squared. If you take that same thing, but you put the axis right down the middle and you spin it like a baton around your finger or arm or whatever, then it's a solid cylinder or disc about a central diameter, okay? So that changes everything, and you have to do a couple of calculations to figure out what your moment of inertia is, and it's m over 4 times r squared plus the total mass times the length squared divided by 12, okay? So, like I said, these can get kind of complicated. We've got a thin rod with an axis, and if it's a pencil or a square piece of iron that's long and thin, that's the same, okay? You can think of it all as the same. You measure the length, you measure the mass, and then you multiply the length squared times the mass and you divide by 12. If you're going to have it go around the center, okay? It has to be right in the middle for that. If you move to the right, you can move that to the right here, and you'll see that the same object, but now we're rotating it on its end. So it's like you take your pencil, you hold one very end of the pencil, and then you spin it around, okay? And that's what we're doing. And in that case, the moment of inertia is the mass of the object times the length of the object squared divided by 3. So it goes up quite a bit when you do that. That leads us to a solid sphere. I talked to you about a solid sphere when we talked about the moment of inertia of the Earth. Its I equals 2/5 the mass of the object times the radius of the object squared. Okay, we can then do a thin spherical shell. Okay, so that means it's a hollow sphere, and it's a very thin shell, and that's 2/3 mr squared. And then we've got a hoop, much like we had up above. So I don't know why they didn't put the hoop next to the other hoop, but they didn't. They probably should fix that in the 3rd edition. Anyway, if you're going to take that hoop and you're going to rotate it around its center axis like this, then you have mr squared over 2. And then lastly, we've got a slab with A and B, and we're doing a slab, okay? And if you notice, it's very much like a thin rod, but it's a thin rod in 2 different dimensions. So it's just a 2-dimensional thin rod, basically. Okay. All right, so do you guys want to know what we're going to do with our experiment? Yes, okay. We're going to do a hoop like the one in the top left. However, we're not going to... Oh, yeah, we will. We'll have an axis where the hoop is like it is in the top left. Then we'll have that same hoop, and we're going to put it up on its axis and spin it around like a wedding ring you spin around on the top of a table. So that's the lower left. We're going to do one of those. I think we're going to do a solid disc. The one top left, second one down, we're going to do a disc. And I think we do a rod, maybe? So we're going to find the moments of inertia for, I think, 3 or 4 objects. The ring. Maybe that's the same. Yeah, 3 or 4 objects. I can't remember. Okay, so let's get back here. Now that we've seen those are pretty much the only ones we're going to use. If you need to on a test, we'll have, they'll be given to you. So you don't have to go into the test with those things on your cheat sheet. Don't you worry about that. Okay. So let's talk about the units for moment of inertia. First, let's make sure I can write. Okay. So moment of inertia. We call it I, and it has units. Well, let's look. What are the units? It's mass times length squared. So mass is in kilograms. Length is in meters. So it would be kilograms meters squared. Okay, and there's no name or somebody famous, nobody like Hook or any of that other stuff to name this unit. So it's just kilograms meters squared, okay? And the symbol is I, capital I. Okay, so let's say if we were in class, I'd be saying, okay, get out your pens and papers and all that stuff. We're going to look at a solid disc. And then I would draw it. Much better. I'm much better drawing in the classroom than I am. That's the point it goes in. So let's erase that bit. And we got to erase a little bit more right there. And then we can have it come out the bottom. Okay, so far so good. We've got a disc. The disc has a radius r, and it's got a height h from there to there. And it's got a couple of axes. This is the first axis, axis 1. But we can also do another axis right down the middle. Boom, 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 boom. And have it come out the other side. So that's axis 2. Okay. So let's say we'll for the sake of all of those who are dying to know how large of an object this is. I don't know why it is. Okay. So the radius is 0.5 meter. The mass of the disk is 42 kilograms. So it's big. It's big and heavy, right? The thickness, H is equal to 0.1 meters. So 10 centimeters. All right, so what is the I for axis 1? That's the question. So we go to our cheat sheet. Let's go to our cheat sheet here. And we've got axis 1. So I know it's not easy to tell, but it's the top left, 1 down. So it's the second one down on the top left. We've got IMR squared over 2. It's the solid cylinder or disk about the cylinder's axis. Okay, that's the one that we're using. So we're going to say I equals 1/2 mass of the disk times its radius squared. So what is that I? Well, it's 1/2 42 times 0.5 squared. Do you guys know what 0.5 squared is? It's not even a trick question. 5 times 5 is 25. And you end up with, it ends up being a quarter, 0.25. So that's kind of nice, but a quarter times 1/2 is an 1/8. So we basically get an 1/8 of 42. And I don't know if you've ever tried to divide 42 by 8, but it doesn't go in evenly. I equals 5.25. And that's kilograms meters squared. Okay. So far, so good. You guys should test me. You should try. Don't trust me. Test me on that. Like, go in there and plug in your numbers and make sure that that works. Okay. So what about axis 2? I for axis 2. So the moment of inertia for our disk on axis 2, we have to go back to our little drawing board. Go back to the graph here. Okay, which one of these is the axis, the thing that we're doing? Okay, it's not a thin rod, it's a solid cylinder or disc, so it'll be on the right, second one down. And it's a solid cylinder or disc about the central diameter. No, we don't want that one. No, we're going to go to thin rod about the axis through the center. Parallel or perpendicular to the length. Okay, that's the one we want. and it's I equals ml squared over 12. Okay, it's a thin rod, but it's not really a thin rod. It's more like a disc. So we're shrinking that L down, but that's the rotation that it's going to be doing. So that's the one we want. I equals ml squared over 12. So let's do it. I equals ml squared over 12. Now, if you remember, L is really our H. Okay, so we'll rewrite it as mh squared over 12. And so now we've got 1/12 times 42 times 0.1 squared. 0.1 squared is 1/100th, so it's 0.01. And we're dividing all that by 12. So essentially we're taking 0.42 and dividing it by 12. So where's my calculator? Where's my trusty, good old trusty? Divide that and we get 0.035. So I equals 0.035 kilogram meters squared. And we can rewrite that the way we properly should rewrite it. I equals 3.5 times 10 to the minus 2 kilogram meters squared. Okay, now let's compare. Let's compare numbers. Which one of these makes the inertia larger? Which one has the larger inertia? Okay, so the moment of inertia for axis 2 is quite small, right here, small. Compared to this one up here, that's bigger, right? We've got 5.25. This thing, just a little section, a little sliver of that is bigger than this small one. So spinning a wheel or a disc, this size of a disc, about its center axis, like the CD we were talking about before, spinning around, that gives us this moment of inertia. And then if we were to spin it like a coin on a desk, so you get your coin on the desk and you hit it with your finger and it spins around like a top for a while, that would be the second, or axis number 2, that would be like that, and its moment of inertia is much smaller. Okay? So those are our two moments of inertia for a disk. So if you think about it, it comes down to how far away are the masses from those little selections of masses, how far are those away from our axis of rotation? And are more of them further away? There's a whole bunch of them. If we go right down this middle axis here, there's a whole bunch of them that are real close. A lot of them are real close. But through this axis, they're all fairly far away, right? Even the ones that are close to this axis, these are over here, those are still far away from the axis number 1, okay? So the further away it is, the larger its moment of inertia, okay? So let's do a little problem-solving strategy. Problem-solving strategy. Let's just get rid of all that. Okay, problem-solving strategy. Okay, we already know the first one, and I think we can move on. So, you got to ask yourself, is torque and mass involved? So if there is torque involved and mass is involved, then if you have a massive object and there's torque, then of course torque equals I alpha, and that means your mass gives you this I, right? And we don't know what that I is. It could be all kinds of things. It could be anything. But you definitely have a moment of inertia if torque is involved, okay? So, 3. Draw a good diagram. Figure out, by looking at what you're seeing, what is the situation. Okay, determine the distribution of mass. So what kind of object is it that we are looking at? Okay, so that's basically what I did when I showed you that figure in the book. I showed you how to determine the distribution of mass. Because you need to know that distribution of mass. 5. What is the moment of inertia for that distribution? You got to find that, okay? So you figure out the distribution of mass, then you need to find what the moment of inertia is for that distribution of mass. What is the angular acceleration? We need to know what is alpha. Okay, and we talked about how you get alpha. We talked about getting alpha many different ways. Alpha equals our acceleration over r. It also equals delta omega over delta t. So, how are you going to get alpha? There's plenty of ways. Even if you have the acceleration, well, of course, if you have the acceleration, you can do that. But you might have F equals ma give you that acceleration, and therefore then you can find alpha. So what is alpha? And you've drawn a good diagram. You found out what I is. We figured out what alpha is. Draw a free body diagram. Now, this isn't just so that you can see your forces. Of course, you want to be able to see your forces, but you also need to see where they're applied, which also means your torque as well. Okay? So it's going to give you not only the forces, free body diagram, not just the forces, it'll provide us the torque. We need to choose our coordinates wisely. Okay, so we might have a stick. It might have a fulcrum right here. We might have a force going this way. We might have a force going this way and a force going this way. We need to say not just is to the right positive and up positive. That's our linear coordinate system. But we also need to say what happens when it moves in these directions. And if this is our pivot point, we need to know if this movement is positive and this movement is negative. Okay? So you define that. It's up to you. But you do it in a good way, a smart way, where you've now done your linear and your rotational coordinate system. Okay? So if you know what alpha is, you can then say, oh, I want my alpha to be in this direction, so I'm going to label, I know it's going that way, so I'm going to label that as positive. Okay, so that's what I mean by choose wisely. Okay, then we apply our sum of the torques. I'm going to rewrite that torque. Don't like that one. Our sum of the torque. You guys are like, well, how is that one any better than the other one? But it is, believe me. Okay, we've got our sum of the torques, but which equals I alpha. We also want to apply our sum of the forces, okay, if it's doing something other than just rotating. Okay, so this is if linear is involved. Linear movement or linear motion is involved. Then we do this as well. Okay, so it could be rolling, for example. Then we've got a linear translation and we've got a rolling situation. Okay, so these two things need to get applied. And then, of course, you want to double check. In the end, you've got some answer. You want to double check. Do a little check. Make sure that it holds together. You can look at it in a different way, maybe, or whatever. But double check or verify that you're not totally off base. And in order to double check, okay, so double checking. Let's talk a little bit about that. If you want to change your pivot point, so we could change our pivot point to be pivot point number 2 instead of pivot point number 1. That's a great way of checking. Okay, so instead of using pivot point number 1, use pivot point number 2. And just pick one, right? And double check. Okay, see if everything still works out. Okay. All right, that's that. Okay, I don't know if I'm going to continue. Let's do an example. Let's stick with this. We're doing fine. Everybody's happy. You can pause. You don't need a break. I need a break. You don't need a break. YouTube pauses. Let's do an example. This is my favorite example of the whole semester. I made this one up. It's called The Boy in the Bowl. Oh, yeah. So there's a boy. He's got to close the gate. All right, so there's a gate. Here's the fence, and there's a gate, okay, and the gate is open, and he's got to swing that thing closed so that the bull, let's see, I'm not going to draw a very good bull. There's a bull over here. We'll make him a round bull. Okay, so the boy has to close the gate before the bull gets out. Okay, so that's the whole point. And the boy has 3 seconds. That bull is going to be out of there. So the time that the boy has is a max of 3 seconds. Now listen, I don't know if you guys had uncles on ranches or any of that other stuff, but I'm going to tell you right now, this boy, his uncle is going to be so mad at him if he lets this bull out. I don't know. I don't even want to talk about what's going to happen to the poor boy. Who knows? I'm not masochistic like that uncle. So he's got to do this, okay? Well, we know that the force of the boy, I don't know, maybe he's only 6 years old. He can only push 100 newtons, okay? Perpendicular to the gate. So what does the perpendicular mean for us? That means that our theta is going to equal 90 degrees. So our sine of theta equals 1, and we don't have to worry about it. Okay, so far so good. So the boy's going to run up to the gate. The bull's going to get out. Oh my God, what are we going to do? We're given the mass of the gate. Mass of gate. We're given it, so that's so good for us. We're going to call it mg, and that is 153 kilograms. Okay, we also know the height of the gate. All right, I'm going to draw the height here. Okay, it's the same height as this bit right here. Okay, it's just different angles. So the height of the gate, that is equal to 1.5 meters. All right, so it's even taller than the boy. So, man, he's got to really get it, push it. We also know that the gate is 2.8 meters wide. Okay, so the width is 2.8 meters. This poor boy, he's got his work cut out for him. I don't know. Better not let it out. So where's the boy applying his force? Of course he's applying it right here. Exactly 2.8 meters away from the fulcrum point, which is right here. Okay, this is the pivot point or fulcrum. Okay. I think we've got everything we need. What are we going to do? How are we going to do this? How are we going to solve this dilemma? Let's give ourselves a little more room here. First, what is the I for the gate? What is the moment of inertia for the gate? All right, a flat rectangle. So that's our first thing that we want to know. We also want to know what is the angular acceleration of the gate. And then third, there's one other thing. Third, how much time does it take for the boy to close the gate? So, will he do it in time? Okay, so here's the one thing I didn't tell you, and that is this angle that he has to close, that angle theta, it's a different theta than this angle theta. Forget about that angle theta. We've got a new one. This angle that he has to close is 50 degrees. Okay, so he's got to get that thing over a distance of 50 degrees to keep that bull in there. It'll lock if he can get it closed. So once it locks, then the bull is in there, he's trapped. But if he doesn't get it locked before the time 3 seconds is up, he's in trouble. So this is our goal in the end, but we're going to get there by figuring out all these other things. Okay, so number one, how do we go about doing that? So we want to use the moment of inertia, believe it or not, for a thin rod. So let's go back. Let's go back to our moment of inertia. And we want a thin rod, but where's the axis going to be? Okay, so the axis is going to be, it's on the right side, the third one down, because the axis is on one of the ends. So it's a thin rod axis through one end. Okay, so it's 1/3 ml squared. So we're going to go back. We're going to take that moment of inertia, and we're going to come back here and go moment of inertia equals 1/3 mass of the gate times L squared. L, we know, is the width. Okay, so let's just call, instead of width, let's delete that, and we'll call it L. Okay, so that's our 2.8 meters. Okay, and the mass of the gate is known, right? Yeah, known. Okay, so we can figure out what that I is. So we're going to say 1/3, 153, and then we've got to square it. Take our 2.8 and square it. And all of that is going to end up being kilograms meters squared. So that's a number. And that number is, convenient. Thank you, trusty calculator. 400 kilograms meters squared. So one thing done. Nice. Okay. What's our next step? Torque. So we're going to do, what is alpha? So torque equals I alpha. But that also equals the force times the distance that the boy is applying. Okay? And we know what the force is that he's able to apply, 100 newtons. And you know he's going to apply all 100 newtons. And the distance is that same length, right? So we've got our force of 100 newtons times L. Great. That's equal to I alpha. So we can solve for alpha by saying the force times the length divided by I, which we've already figured out. So far so good. We're going to get alpha here in a second. Oh boy, what do we got? He can apply 100 and it's 2.8. So 2.8 meters times 100 over I, and I is 400. So 2.8 times 100, that's 2,800. And we're going to divide that by 4. Plug that in, and we get 0.7. And I don't know if you're paying attention, but somewhere along the way, we lost our meters, and we're left with radians per second squared. So we lost our meters, and the ghost of radians appears. Excellent. Good for us. We now know alpha, so we can box that in. Alpha equals 0.7 radians per second squared. All right, let's move up. We need a little more room here. We're going to put the bowl up above so we can't see it because it's frightening. How much time is it going to take? So here's where we get down to our third thing. Number 3. He's got to close the gate. Theta equals 50 degrees. How long is that going to take us? Well, we can use this equation. Theta equals omega naught times t. And if we add 1/2 alpha t squared, then we'll have theta. Okay, so we know what theta is. It's 50 degrees. What is omega naught? Well, that gate is not moving at first. So omega naught equals 0. And we know what alpha is. So we can solve for t using theta equals 1/2 alpha t squared. That'll give us a t, and let's pray. We're going to just pray that homeboy, our little guy, that he doesn't, I don't know what his uncle's going to do to him. Oh my gosh. Okay, so how do we do this? Well, we solve for t. So t equals 2 times theta divided by alpha. Theta. 2 times theta. I said it and then wrote alpha anyway. 2 times theta divided by alpha and the square root. Okay. So let's see. Let's plug in some numbers. 2 times 50 degrees divided by 0.7 radians per second squared. I'm seeing I'm seeing problems here. Uh-oh. We've got degrees here and we've got radians here. What are we going to do? Well, we got to convert. We've got to convert that 50 degrees into radians of somehow. Okay? So, do you guys remember? I'm going to do it off to the side here. 360 degrees over 2 pi radians equals 1. Okay? So, we can flip that and say 2 pi radians equals 360 degrees. So we can do 6.28 radians divided by 360 degrees. That'll get rid of our degrees, and it'll give us our angle 50 in radians instead. All right, so let's do that. Where's my calculator? Here it is. Okay, 2 pi divided by 360, 0.87 radians. Okay, good. Now we can get back to business. We'll erase our uh-oh. We'll erase this, and we'll get back to 0.87. And then we'll take the square root of all of that. So again, calculator time. And we've got 1.58 seconds equals our time. Whew. He did it. The bull never had a chance. The bull never had a chance. Did you guys think I would design this where the kid gets spanked or whatever? I don't know what would happen, but yeah, I'm not gonna do that to anybody. So okay, let's stop there, and we'll go on to the next one. Thank you for watching.